Okay. So we are in fact at day 30. Um, yeah, it's kind of surprising to be here. Um, I certainly thought I would be completed by now. I think my initial progress on the conceptual side kind of fooled me for how far I was um, in being able to complete something like this. And realistically, I still haven't made tremendous effort on the practical side for doing calculus. So there's that. Um, right now, we're just kind of going through steps to understand the test. Um, but all in all, it has been good. In my personal, or I guess my non-streaming learning, I've been implementing a lot more testing because testing is all things being equal. I think it's like a 50% increase in learning. That was from a podcast that I listened to, and yeah. So, being that that's the case, I guess I haven't seen the study, but being that that's the case, it's wise to test a lot more. Um, and I've not only tested in my learning, but I've also worked to test while I'm programming to deliberately create a hypothesis or make it clear by writing it down, even, and then testing my hypothesis. And that's been good. I obviously like that is done, obviously within programming generally, but I've wanted to make more of a deliberate effort with it, and that's also been fruitful. I remember last time I was worried about the trigonometric functions, thinking that I didn't have them down as well as I would like, but I actually remembered them much more than than I was expecting. So that was kind of a pleasant surprise. We'll see if that holds. But I think the understanding of the unit circle really kicked off my understanding of the trigonometric functions generally. That was kind of an aha moment for me. Okay, so yeah, I think we'll just continue chugging along. First, we'll do our Anki, and then I think we are just at 3 here. Slowly but surely. Okay. And I think I did that. Deep dive on finding limits. I think I should edit that card. Oh shit, you guys can't see. Okay, here we are. Anyway, so yeah, we're gonna keep chugging along on this, but first we will do the. Oh, actually, first I think I'm gonna grab some water, and then we'll dive into our cards, and then we'll continue on the test. And I think the test only has 5, like, question. Yeah, it only has 5 questions, even though it has a bazillion. Oh, sorry, 6 questions, even though it has a bazillion sub questions. But it's still only 6 questions. Okay, I'll be right back. Okay. Okay, the mean value theorem. Okay, this is the notion that for a given function, for a given secant line of a function, there is a tangent line that matches the same slope when the function is continuous on a closed continuous on a closed, oh, what is that called? Closed or open? I forgot what that is. And differentiable on an, or sorry, continuous on an open, and then close. Let's see. Open versus closed interval. Interval. That's what it's called. Okay. So it's differentiable on a closed interval and continuous. Sorry. Yeah, continuous on a closed interval and differentiable on an open interval. Differentiable on continuous. Okay. We're going to send that one through again. The derivative of tangent of x. Oh, this is the odd one. I think negative secant of x, or secant squared of x. Okay. This one is not great. So secant squared of x. This is probably the most unique one. Maybe going through the proof here for this. For what and how get the derivative of tangent of x. Okay. Okay, so we start with the tangent function. Okay, and then we have the quotient rule, so we have sine over cosine. Oh, we're doing something more than I thought. Okay, I've never interacted with the quotient rule, I don't think. This is completely new to my knowledge. Shoot. That's another thing that I thought I was, well, I guess it is what it is kind of thing. Okay. Yeah, I don't have any quotient rule. Oh. Let's restate in less than 50 words. Okay, so the quotient rule, calculus is a formula for finding the derivative of a function that is the quotient of two functions. Okay. is negative secant squared of x. The derivative of cosine, I believe, is negative sine of x. The cotangent reciprocal identity states that, or the cotangent reciprocal. Oh, cotangent is equal to 1 over tangent of theta, right? What's U substitution and calculus? So this is another name for the reverse chain rule. And this is where if we have a form of f prime of g of x times g prime of x, then we can reverse it into f of g of x, and that would be the integration of it. The integration method that simplifies a complex integral by substituting a part. Okay, so this is the process for it. I guess I won't be tested on. Yeah, so I'm fine with that. Why is it the case that the vertical asymptotes can be found through considering the denominator? Because as a denominator gets arbitrarily close to 0, the resulting number approaches infinity. Okay, so this is, I believe, f prime of g of x, or the form required is f prime g of x multiplied by g prime of x, and that can be moved back into f of g of x. Okay. The reverse chain rule is a technique for integration, also called U substitution, where you identify an inner function and its derivative, allowing you to integrate a composite function by reversing the chain rule from differentiation. It's used to simplify and evaluate integrals of the form. So it's f of g of x times g prime of x. Okay, got that wrong. Yeah, yep, okay. So if you don't have an exponential function, or the function isn't a power of x, I think I misspoke that. The antiderivative of cosine. So the derivative of cosine is negative sine of x. The antiderivative, I'm not sure. Oh, it's just sine. Interesting. Okay. So the derivative of cosine is negative sine, and the antiderivative is just sine. Yeah, okay. This formula, sine 2 squared theta, and I'm trying to, I'd like to do a test outside of this test, but this is a double angle formula. But sine of 2 theta is equal to 2 times sine theta times cosine theta. Okay? The definition for cosecant is it would be 1 over sine which would be 1 over y. The quotient rule, this is the one. Let's look at this beast. Okay, the quotient rule in calculus is a formula for finding the derivative of a function that is the quotient of two functions. For f of x, u of x over v of x, the derivative is u prime of x times v of x minus u of x times v prime of x, v over v vx squared, v of x squared. Okay. Okay, I think I'd like to, we're just gonna, we are going to need, okay, so that one's done. That one's done. I need to go through the quotient rule more. Okay. The secant line goes through 2 points. And tangent line... Oh, I think this is a bad explanation. The secant line goes through 2 points and the tangent line goes through 1. Okay. I feel like this isn't great. Let's see. If we get something similar, then I think this is better than I think. But this just feels incorrect. Or not incorrect, but not... Okay. Okay. We get the same thing here, so I think this is fine. The derivative of the sine of x would be cosine of x. Yes, okay. Because the derivative of cosine is, or better said, the antiderivative of cosine is sine of x. And so I know that the derivative of sine of x is cosine. The derivative operator in calculus is d over dx. For rational functions, just see where the denominator goes to 0. And, yep. An integrand is a function to be integrated. A rational number is one in which does not have any square roots, and is non-repeating infinite. The antiderivative of sine of x is cosine. For non-rational functions, I think for this one, you just see where y approaches negative and positive infinity for a finite number. Okay. So it does say find where it's undefined or discontinuous. So I was sort of close. We're going to send that through, though. Again, it does make sense that we look for something. We look for something undefined or discontinuous. Mean value theorem states that for a given secant line, there is a tangent line that is equal to it. If it is the case, under these two conditions, that were continuous or are closed, continuous on a closed and differentiable on an open interval. Continuous on a closed and differentiable on an open. Okay. A radical is a square root sign. Or, yeah. I guess it's a root sign because square is just a particular variety of that. If the function does not have an exponent of x, function isn't a power of x. That's a better way to say it. This is a rule that takes you back from a particular form to f of g of x. The form is f of g of x times g prime of x. So you reverse it. The antiderivative of cosine is sine of x. The quotient rule in calculus, this is one that allows us to have an idea for it allows us to differentiate two functions where one is, or I guess, where one is being divided by another. Okay, so I have an idea. Actually, oh no, I don't think that's the case. So I was thinking that this might relate to the chain rule. Oh, actually, no, that's certainly not the case. Never mind. Because chain rules refer to only composite functions. This is unique. Okay. So interesting. Okay, so u prime of x times v of x minus u of x times u prime of x over v of x squared. So we'll run that back through. For non-rational functions, you look for discontinuous or undefined points and see if they approach infinity from the left and right. If you don't have a function that has a power of x, when the function isn't a power of x. Okay. The quotient rule is finding the derivative for a rational function, u of x over v of x, and this is u prime of x times v of x minus u of x times v prime of x over v of x squared. Okay. Nice. Okay, so now we hop on. Okay, so state the domain and range of the function. So I feel like we hop down a little rabbit hole, but I okay, this is squeeze theorem. I think we already did that. So maybe, okay, let's see. Within calculus, we're just going to do a new chat. I love how I created this, but I've never even used it. I have 3 chats here. Lamau. Oops. But I also don't think, well, I guess I could, we'll just keep going with what we're doing. We will not worry about it. Okay, so, in calculus, how do I find this? How do I, okay, so, so it is the case that, okay. Oh, okay. Okay. So, for the domain, okay. Yeah. Okay, so for the domain and range of function, a domain is all the possible input values that are defined within the function, and I guess the range would be the possible output values. So the range would be non-infinite in situations where the function is bounded. So if the function is bounded, then obviously the above or below the upper and lower bounds, respectively, we'd have values that aren't defined within the function. Additionally, if we have if we have discontinuities and undefined parts or undefined values within, undefined points within the function, then we would have one that doesn't exist, or sorry, an input that doesn't exist in the domain because it's not defined for it, and then an output that doesn't exist within the output because it's not defined. Okay. So I feel pretty confident being able to do that. We'd have to find the input or the whatchamacallit, whether or not a function's bounded. And we'd also have to find if there's any undefined points. Okay, so let's see if that's correct. Okay. Is defined. Okay, perfect. Oh, okay. So this is only for defined. So I think I might have misspoke, or I wasn't being precise. That for an input, if we have a discontinuity, that's fine on the input side. As long as the input is not undefined, then we're like being chilling. Okay, range. Okay, let's see. So we start with the set of all real numbers. Exclude x values that make the denominator 0, cause square roots of negative numbers, cause logarithms of non-positive numbers. Intersection of all such constraints gives the domain. Okay, right, so we use some builder notion, set builder notation. Ite. So we're describing open intervals and closed intervals. Okay. Range. The range is the set of all real numbers such that... Oh. Okay, the set of all real numbers y such that y equals f of x for some x in the domain. Steps to determine the range. Solve y equals f of x and find all possible values y can take. Algebraic method. If invertible, try solving y equals f of x for x to determine which values of y the inverse for which values of y the inverse makes sense. Use derivatives to find the local extrema and minima and maxima. Analyze end behavior. Graphing visual inspection can confirm or guide algebraic work. Okay. Domain. It all makes sense. Input constraints. Range of values range of f of x or values that can actually produce output behavior. Use algebra and calculus to derive both rigorously. Okay. So I didn't think about the algebraic method. And I didn't think about, or had no, well, could you help me understand why, for the calculus methods, you have used derivatives to find local extrema? I would think that for finding the range, we would just be concerned about whether or not we have a bounded function. Is that the case? Question mark? Whether it's infinite or not. To find the exact values a function can take, we need more detail. That's why derivatives and local extrema come in. The first derivative tells us where the function increases or decreases, and where it might have local maxima or minima. If a function has a minimum or maximum, those values bound the range. You can't fully describe the range of a function unless you know where it starts and stops changing. Okay. If a function has a minimum or maximum, those values bound the range. You can't fully describe the range of a function unless you know where it starts and stops changing. Let's say f of x equals x squared minus 2x plus 3. First we take the derivative, 2x minus 2, set it to 0. Check this is a minimum by the second derivative test. Plug in x equals 1. Since the function opens upward, positive coefficient on x squared, it goes to infinity on either side, so the range is 2. We could not have concluded this exact range from boundedness alone. We need the local minimum. We know it's bounded. How do we know that 1 is the minimum, or sorry, 1 is the maximum? Take the derivative. Okay. Plug in x equals 0. So the maximum is 1, and it decreases on both sides from there. This is just the second example. Okay. Boundedness tells you whether the range is infinite or is finite or infinite. Derivatives help find local minima / maxima, which often define the exact bounds of the range. Yep. Okay. Okay. This is this is totally reasonable. Okay. We will add this. Okay, so this has like a lot of parts. I don't know if I like this. So the issue here is we're identifying all the real numbers where the function is defined. Exclude values that cause division by 0, roots of negatives, logarithms of non-positives. So, okay, find all the, okay, I think I'm good without this. If I know that a function is defined, is a function defined at a given point if it does not cause division by 0, does not cause even roots of negatives, and does not cause logarithms of non-positives, question mark? Oh yeah, piecewise functions. Okay. I think this is fine, and then this will just be a little extra sauce. Okay. Yeah. I'm fine with that. Okie dokin'. Okay, so given what we know so far on this, let's okay, so back to the question of range of a function's range. What does it look like when you take the minimum, maximum, and the function's range is negative inf to positive inf. Okay. Okay, so I need to recall the operation that we do for finding the min or max function. So we find the local minima. Sorry, or the local extrema. These are possible places where. Oh, okay. It just all came back to me. So for local extrema, we take the we take the first degree derivative function and then plug in 0. Take that value and plug it into the second derivative, or second. Yeah, let's see. We would plug that in. So, okay, we take the derivative, set it to 0, check if this is a minimum by the second derivative test, plug in x equals 1. Yes, okay. Okay. Okay, I feel good about that. Yeah, Okay. So, I think I'm going to try to get this one solved, and then we will yeah, so we'll go through this first. Domain of the function Okay, so for the domain of the function, oops, let's swing that over here. Okay. Okay, the domain of the function is the excluse, or the open interval of negative infinity to positive infinity. The reason being for this is that there are no points in this function where a given input is undefined. There is no situation where given input is undefined. Okay. Now let's recall what was said earlier on the test, not the test one. Recall what was said earlier on the Anki card I just did about the determining or finding the domain. So for here, we check if there's anything undefined. If it is, then we know it does not exist within the domain. Okay. And then for that, we look for situations in this. Let's see. The reason... yeah, I don't know how to say, like, do I just make explicit that, like, there are three cases, you know, where one, we have a 0, or we're dividing by 0. 2, we have like a negative number underneath a radical, like a square radical. Or then 3, the logarithm situation, which I forgot. Okay. They only do... Okay. Okay, so this one will be we're gonna find the minima and maxima, and this is done through getting the first degree derivative test where we set it to 0, take that number and plug it in to the second degree derivative. If that is greater than 0, we know I forgot about which way that goes. One of them is greater than 0, and one of them is less than 0. I think for those that are greater than 0, that's the local minima. Or sorry, that's the minima. And for those that are less than 0 is the maxima. I believe that's correct. Okay. Okay, yeah, so that's the minimum value is 2. And so since it opens upward, because, yeah, if it's positive, then it's the minimum. Okay, the range is 2, yeah. Okay. Okay, oh, let's go back and see this, though. New. Division by 0, even roots of negatives. Oh, yeah, that's actually a better way to say it, because 4 and 6 would also be that. or logarithms of non-positives. Okay, so points where a given function is undefined. For example, I don't know. So the issue I'm having here is, I don't know how to like prove that it's the case that, all x's are defined here, right? I know that we're not dividing by 0. I know it's not a piecewise function. I know that we don't have any logarithms of non-positives, and we don't have any negative roots. We don't have any, negative roots of, we don't have any negatives under an even root. So I know those situations are the case, right? But, actually, I don't think the piecewise function one is correct. Oops. Okay. So I'm going to test that and see if that's correct. There's no points in this function where a given input is undefined. Okay. Yeah, I just don't know if that's enough because typically in like mathematics stuff, you have to have like more reasoning outside of just these 4 instances aren't the case, right? Instead of asserting like if I had a particular, this is a obviously contrived example, but if I had a prime number, if I had a number that happened to be a prime number, and I am asking, the question is this a prime number or not? And I say, oh, well, it isn't 3, it isn't 5, it isn't 7, so it's not a prime number. Right, I don't know if, for the domain, I don't know how to specify that. So we'll just say there are points in the function where the given input is undefined, where when the result of an input is undefined, where the result of an input is undefined, additionally, this is the case because there are no possibilities of dividing by 0. No negative. What is the way for saying that? Negative of an even root. Even roots of negatives. That's a good way to say it. No even roots of negatives. And no negative logarithms. No logarithms. Okay. Is this sufficient? Justification. Oh. Okay. So, more about the nature of it being a polynomial function. I think that's reasonable. Okay. Okay. The reason for this is this function is a polynomial, and polynomials and polynomial functions are always defined. Okay, so I guess the way to I guess the approach here was, instead of identifying three ways in which we could exclude this from being like negative infinity to positive infinity, instead of saying, oh, those three ways that we find if the the domain is not negative infinity to positive infinity, those three ways don't exist within this function. So therefore, its domain is negative infinity to positive infinity. So the better approach here is, instead of giving those the lack of exclusion criteria, what is instead is that we're looking at the composition of the parts of the function and determining if any of these could be undefined. So for this here, for the function here, we have a polynomial. Like this, the entire function is it's a polynomial function, and polynomials are always defined, and so it is the case that because all the polynomials will always be defined, we know that the function is defined. So instead of justification by exclusion, we're doing by actually it's not even exclusion. Well, it is exclusion. So instead of justification by the lack of exclusion criteria, we are justifying by the composition of the function, which is, a much better justification. So I think that's totally reasonable and fair. Okay, we are at 17. So I'm going to call it for tonight. This has been a good session. Yeah, it's been good. I'm going to just bring this over here so we know where we're at. And then we will continue from that point tomorrow. Yep. Sweet. Okay. I'll see you guys later.